Hello students, welcome to lecture 23 of the online course on Nanophotonics, Plasmonics and Metamaterials. Today's lecture will be on effective medium theories. Now if you remember the discussion on electrotunable optical devices where we discussed nanoparticles in aqueous medium or any other kind of mixtures kind of cases where nanoparticles or any other dielectric nanoparticles which are scattered in a homogeneous medium, in those cases there is a requirement of estimating the effective permittivity of those medium. So this is where this kind of theories will be very much applicable. So today we will quickly look into certain things like different classifications of engineered materials, and here we will particularly focus on the mixtures and how do we characterize those mixtures in terms of their effective permittivity, and we will look into these effective medium theories. We will introduce this concept, then we talk about Wiener bounds, we will discuss about Maxwell-Gardner theory, Bregmann's theory, and also Nicholson-Ross-Ware or NRW method. So, I believe you know this particular slide now. So, these are the different classifications of the engineered materials. So, in this lecture we will be mainly focusing on mixtures. So, mixtures are basically they are made of ordinary materials which are combined together to get some averaged property. So, that is very important here. So, we are looking for some averaged property in this case. Okay. So, what are the mixing rules for these mixtures or engineered materials? Now, if you wish to mix multiple materials together to get some overall material property, there has to be some kind of guidance through which we should achieve that, like some kind of formula that relates the effective permittivity to the permittivity of the constituent materials, and that will be seen here. So, the effective dielectric constant of the mixture can be taken as epsilon effective, and that depends on couple of things. Okay. So, something like the shape of the materials, then the size of the particles, electromagnetic properties of the particles, statistics of the particle distribution, and the volume fraction of the constituent materials. So, how much volume one particular material is covering, that also plays a very important role. Okay. So, effective medium theories, as I mentioned, why they are needed. So, effective medium theories can provide a macroscopic model of inhomogeneous media based on analytical, numerical and sometimes experimental techniques. So, these are basically a description of composite materials in terms of effective medium approximations. Okay. And this is basically a very important tool, as I told you, it is a valuable and versatile tool that allows you to investigate, predict and design the electromagnetic response of natural and structured materials. Now, effective medium models, they equip the macroscopic Maxwell's equation with very simple constitutive relations. So, that is where you take care of the light matter interaction, and in that case you do not need to go into the complexity of looking into all the minute details of light matter interaction at the constituent level. Rather, you can actually deal with the macroscopic Maxwell's equation on a averaged manner for a particular mixture. So, when approaching an electromagnetic problem with effective medium theory, what is very important is to know the limits in which this theory is valid. So, that is basically coming from that bounds are called as Wiener bounds, which we will see in the next slide. So, if you push the effective medium theory beyond these limits, obviously it will fail. So, you will not get correct predictions, rather you may get wrong predictions. Okay. And effective medium theory usually depend on the electric and magnetic properties of the constituent materials, the volume fraction of each constituent, and in some case the geometry of the structure at the constituent level also gets into this particular theory. we'll look into the different theories and different cases where each of these theories can be used. So, the fundamental limitation of this model, always you have to remember that every theory is valid for a certain range, but then it also fails beyond certain limit, and also there are some limitation or approximation, or you can say simplification, that has been considered while deriving these theories. So, first thing is that when you are looking for any approach for homogenizing the structured materials, it is always the underlying assumption that the wavelength of the light is much larger than the characteristic scale of the inhomogeneity. So, in other words, you can say all those inhomogeneity is basically much smaller than the wavelength of light, or they are simply sub-wavelength in nature. Now, depending on the size, permittivity and permeability of the constituents, as well as the index of the hosting medium or the background medium, the limitations of the model can be more strict or less strict. Okay. So, here is one example. So, here you see you have a host medium with permittivity epsilon h, and then there is, it has got some inclusions which are basically nanoparticles. Now, these are two different types of nanoparticles being mixed here. So, one is type 1 nanoparticles, which is given as epsilon 1 Np is the permittivity of that nanoparticle, and the other type is this one that has got a permittivity of epsilon 2 Np. Okay. And then these are all homogeneously distributed, or you can say they are randomly distributed, does not matter, the distribution does not matter here. Okay. They are into this host medium, and effective medium theory will be able to give you a epsilon effective of this composite system, which has got a background medium and two different type of constituent materials, but you will be able to get a effective permittivity using the effective medium theory. Okay. So, we will actually look into this aspect in today's lecture. So, as I mentioned, for mixtures there exist limits on the range of possible effective permittivity values. So, when you mix 2 or 3 different materials, you cannot get very abrupt or out of the world permittivity values. No, that is not possible. So, you can actually get some effective values which are limited by some upper bounds and lower bounds. So, those bounds are known as Wiener bounds. Okay. So, there are some formula that helps you to find out what is that minimum permittivity and maximum permittivity. So, if you consider a 2 component system, it means you have one material and the other material. So, one material is filling a fraction of F in the volume. So, the fraction for the other material is obviously 1 minus F, and this is how you find out, this formula tells you how do you find out the minimum limit. Similarly, you can also find out what could be the maximum permittivity for this kind of a system. So, if you think of a multi-component system, there also you can find out what is the minimum permittivity. So, here instead of F you will have Fm. So, this is the fraction of the volume occupied by that material of M index. So, now all the fractions, if there is a 2, 3 or 4 different materials, so it will be like F1, F2, F3 and F4 should add up to 1. In this case it is only 2 variables. So, here F1 plus F2 equals 1. Okay. So, you will get this formula basically. So, if you take one as F, the other is basically 1 minus F, and that you have seen here. So, this is the formula that tells you about the minimum permittivity and maximum permittivity for the case of a multi-component system. Okay. And now, when you plot this, if you take a 2 component system and you take epsilon R1 equals 200 and epsilon R2 equals 2.5. Okay. So, if you take this, so it is basically like 2.5 is basically the background medium, and then you have dielectric nanoparticle, very high dielectric high permittivity dielectric nanoparticle inclusions. Okay, in that case you can see this is how your epsilon max will be, and this is how the minimum will be. Okay, so the minimum value can go to it's here. So you can actually when you keep on increasing the volume fraction, okay, that is when you are making f is close to 1, you can go up to 200, and when you make f equals 0, that is that dielectric inclusions in the host permittivity is negligible. In that case the effective permittivity is nothing but same as the host permittivity, which is epsilon R2, that is 2.5. Clear? So with that, these are the bounds within which the effective permittivity will be. So all these values are possible depending on what fraction you choose. Okay, that is how you can always go and find this region is allowed. Okay, so that is how mixing can give you that many possibilities. Now let us look into one of the most popular effective medium theories, which is called Maxwell-Garnett theory. Okay, so this is the classical approach for homogenizing media, which has got small inclusions dispersed in a continuous medium or matrix. So one particular schematic will make it clear. So it is like this: the basic structure is a two-phase medium with separated grains of the guest material. So here you see the guest material is this one, which is got a permittivity of epsilon I. The host medium has got a permittivity of epsilon H, okay, and you are supposed to find out the effective permittivity of this particular system, okay, using some theory, and this is where Maxwell-Garnett theory will come into the picture. So we restrict the analysis to the case of non-magnetic and isotropic materials. So there are some assumptions. So initially I mentioned about the assumptions. So here the assumptions are that the materials we considered are non-magnetic and isotropic. So how do you start with that? First thing, if those inclusions, the small islands, are sub-wavelength in nature, so you can easily adapt quasi-static approximation, that you have already understood in previous lectures. So in that case, if you see that the inclusions are positive permittivity inclusions, okay, then the following rule of thumb is considered to be conservative. So you can actually go with this rule that the particle size should not exceed 1/10 of the effective wavelength. So it should be less than lambda by 10, okay, and lambda is what? That is at this particular wavelength you are measuring the effective medium permittivity. And if you get a metallic or negative permittivity inclusions, the limit of the validity is much more stricter, okay, and this is the reason here is that because this negative permittivity materials, as we have discussed before, they can show localized surface plasmon resonance. So in this case you need to be very careful about this particular particle size limit, okay. So let us see how do we go about that. So in case you do not have this information about the shape of the inclusion, okay, so the shape can be any arbitrary shape. So the natural approach would be to assume each of those as very tiny spheres, okay, and that is how you can actually see how Maxwell-Garnett homogenization work. So you can consider each of these inclusions as spheres of different size, and if the material is excited by an external electric field, so in quasi-static approximation we can understand that in this case, the field on each of these tiny spheres that we have considered, the field will be static, and that is why it is called quasi-static approximation, right. And we are considering the external field to be EE, okay, that is the notation we are using here, EE, okay. So first we will, so let us see into the derivation of this formula. how Maxwell-Garnett theory helps us in getting the epsilon effective. Okay. So, first of all we have to focus on the response of each isolated sphere to this excitation. So, there is an electric field, and to this how these isolated spheres are responding. Okay. Now, we have seen that when the sphere is very small, it just acts as a point source with an electric dipole moment proportional to the applied field, and that will be at the center of the particle. So, you can write that response of an isolated sphere where the host medium is epsilon h. So, that isolated sphere can be written as pH equals epsilon naught epsilon h alpha E. Okay. Now, what is epsilon naught? That is the vacuum permittivity, okay, and alpha is basically the static electric polarizability of the spheres that you have considered. So, this you remember from the quasi-static formula, that alpha is basically 3V times epsilon I, that is the material of that sphere, minus epsilon h over epsilon I plus 2 epsilon h, okay, and V, what is V? V is the volume of that sphere. Okay. So, now once we have this formula, we can always write what is the electric field inside the sphere, and that will be 3h over epsilon I plus 2 epsilon h times epsilon E, and we consider this field to be uniform and parallel to the external electric field E. Okay. So, with these two things we have also seen that the polarizability, because the sphere is very tiny, the polarizability of the sphere is considered to be isotropic, since both permittivity and the shape are assumed to be isotropic. So, polarizability is also isotropic. So, what comes as the next step would be to create an effective model of the distribution of the nanospheres. So, that allows you to give you this kind of a homogenization picture. Now, the spheres are now reduced to point dipoles. You can consider them as electric point dipoles, and the field they are radiated, okay, each dipole is radiating, will influence the all other dipoles in that particular medium. So, in such a case you need to get an information about how many such dipoles are there in unit volume. So, let us assume that there are n such dipoles in that unit volume. So, now you can define the effective permittivity based on the average or macroscopic constitution relationship that would link your displacement field, the average displacement field, to the average electric field. Normally what happens, D equals epsilon E. So, that is where the epsilon comes into the picture. So, in this case the D displacement field is also the average field, the electric field is also the average field. So, epsilon will be now the effective permittivity of that medium, right. So, the average operator integrates over sufficiently large volumes to provide an accurate description of the average fields of the original medium, and so you can write this particular expression. So, you can write average D is nothing but epsilon naught epsilon mg. So, epsilon mg is nothing but the Maxwell-Garnett effective permittivity of this particular system, and then multiplied by the average electric field. And you can also see that this we have understood that this dielectric displacement field has got actually two parts. One is the average response of the host medium. So, this is from the host medium alone, and plus there is some average response of the point dipoles, which are basically the inclusions, right. So, if you look into the point dipoles, this point dipoles the average polarization is basically n times small p, and here remember that this small p is not same as that isolated spheres polarization or dipole moment. Okay. Here this small p is basically the dipole moment that is calculated in the presence of all other dipoles in that system. Okay. So, the evaluation of this small p is classically performed by evaluating the local electric field, which is denoted by EL, and this is the local electric field which is felt or experienced by each point dipole in the presence of all other dipoles. Okay. So, the field, this local electric field is basically the average field augmented by a contribution due to the average polarization that surrounds each dipole, and this is also known as the Lorentz field. Okay. Now, how do you find out this EL? To find out EL acting on a single dipole, a simple model of the mixture can be adopted, where a fictitious spherical boundary like this is can separate, okay, this dipole from the background media. Now, this background media has got a average polarization of P, okay, and there is a average electric field of E, but this dipole is in a kind of spherical boundary which is separated from this macroscopic background. So, with that you can write down local electric field EL will be nothing but the average electric field plus the polarization divided by 3 epsilon naught epsilon h, and from that you can also write down what is the dipole moment small p, that is given by this expression. Now, in this expression, when you put your you can, from this you can retrieve the Maxwell-Gardner permittivity in terms of polarizability alpha and number density n. So, you can write epsilon mg is nothing but the host permittivity 1 plus n alpha over 1 minus n alpha by 3. So, I am not showing the overall calculation here, but this can be obtained from this formula. And in the case of very diluted media, you can consider, so n is very diluted media means n is very small, capital N is very small. So, you can actually consider these as close to 1. So, in that case the effective permittivity will be simply epsilon h 1 plus alpha n. So, this is how you can find out the effective permittivity, and the same expression can be easily obtained when you put that your local electric field is only this one. So, the contributions from the neighboring dipoles are also negligible. So, this kind of approximation is fully justified in the case of a diluted mixture where the interactions between the dipoles is weak. That means, when the spheres that you have seen are far away from each other, that they do not interact with each other. In that case also, in that case this particular approximation will be valid, and using this formula you should be able to find out the effective permittivity very easily. Okay. Now, you have seen this particular case that Na by 3. So, from this you can find out this one, and then you can also write that Na by 3 equals epsilon mg minus epsilon h over epsilon mg plus 2 epsilon h. Okay, that is coming from this equation. Okay, and this equation is also known as the Clausius-Mussoti formula, or it is also called as Maxwell's formula or Lorentz formula. Okay. Now, in this one, if you put alpha from the quasi-static theory, that is alpha equals 3v epsilon I minus epsilon h over epsilon I plus 2 epsilon h, okay, you will be able to get this kind of a formula, which is also known as Rayleigh formula. Okay. So, in this, what is epsilon mg? That is basically the effective permittivity of this medium. And what is f, small f? F is basically NV, that is the volume fraction of the inclusions, and in this case it is sphere. So, from that you can find out what is the effective permittivity, that is epsilon mg in terms of epsilon I, epsilon h and f. So, these are the three things you got to know. You should know the permittivity of the host medium, permittivity of the inclusions, and the filling fraction of this material in this entire volume. So, you add up all these volumes, okay, and divide by the total volume, that is your filling fraction. Fine. So, this simple formula represents a classical approach to homogenization of the composite media, and it is widely used in many applications. Remember, here we have to make sure that the nanoparticles are far away from each other, so that they are not interacting. Okay. So, this is the case. Now, it is also important to notice that the only necessary parameter for retrieving the Maxwell's Garnet permittivity are basically three things, okay, as I mentioned, the volume fraction and the two permittivities, and this formula does not require the spheres to be of the same size and they should be located at a specific location. So, all these requirements are not there. So, you do not want your spheres particularly to form an array or something, nothing like that. So, the only requirement here is that the wavelength in the medium must be much larger than the size of the inclusion, so that the quasi-static approximation remains valid. So, Maxwell-Garnet theory also predicts the following. So, if you put f equals 0, you get effective permittivity to be same as the host one, and if you put f equals 1, you will get the effective permittivity to be same as the inclusions 1. Okay, that is pretty simple. So, that tells you about the Maxwell's-Garnet theory. The next important and popular theory is Bregmann's theory. So, we have seen that Maxwell-Garnet formula represents a valid homogenization model for mixtures with a well defined host medium and inclusions, right, and they result more accurately for small values of inclusion volume factor f. So, smaller the f is, you will get more and more accurate result. Now, there could be aggregate mixtures which has got random distribution of two or more constitutive materials, and in those case the effective medium theories should be based on some statistical formulation, right, and these are the cases where you have continuous boundaries and any of this material can be of any permittivity and they may have a different fill factor, right. So, these are the cases where you actually use Bregmann's theory. So, here also what you will do, you will try to find a medium. So, you will try to find what is epsilon Br, that is the effective medium. So, you have the host medium and the inclusion medium, they are basically capturing different regions. So, you will see that how do we handle this particular class of inhomogeneous mixture through Bregmann's theory. So, let us consider two phase microstructure of the type that is shown in this figure, where the constituent material of permittivity epsilon I has filled a volume factor f, and in that case the other permittivity material epsilon h will have a volume fill factor of 1 minus f. Okay. So, this mixture will be now modeled as a continuous medium hosting a distribution of small and large spherical inclusions of the two different dielectric permittivities. So, one is h, epsilon h, another one is epsilon I, okay, and the background one or the overall one is basically epsilon Br, not the background one, the overall or the effective one. So, the probabilities of finding spheres of permittivity epsilon I will be f, and for finding permittivity spheres with permittivity epsilon h, the probability is 1 minus f. Okay. So, this basically corresponds to their volume fill factors in the original mixture. Now, we can assume that the host medium for this Bregmann mixture has unknown effective permittivity. So, what is that? That effective permittivity we write as epsilon Br. Okay. So, how this will be related? So, you can write down the basic form of the Bregmann theory as f times epsilon I minus epsilon Br over epsilon I plus 2 epsilon Br, okay, plus 1 minus f times this. So, if you see, can you find out what are these basically? These are basically the contributions coming from spheres of permittivity epsilon I in a effective background medium of this one, plus the volume fraction of the other type of spheres which has got permittivity of epsilon h in a background of epsilon Br. So, this is how you add up these two contributions, okay, and that is basically the basic form of the Bregmann's theory. Now, if you have more inclusions, not only two, say if you have a multi-phase aggregate, in that case it will be simply summation small m equals 1 to capital M f m epsilon m minus epsilon br over epsilon m plus 2 epsilon br equals 0. So, what is Fm? Fm is the filling factor or volume fill fraction of the mth constituent of the mixture, and there are total m number of capital M number of phases, right. So, the limitation of the Maxwell-Garnett theory that the particles with very small depolarization factors. Now, what do you mean by depolarization factor? A low depolarization factor means it actually polarizes. Okay, so you may think of elongated shapes like ellipsoids and all these things, and this kind of shapes, they may result in strong particle interaction. And as I mentioned previously, that in Maxwell-Garnett you do not actually like those kind of contributions or interactions to come into play. So, in this situation, which is similar to the situation of a mixture of large inclusions fill factor, the Bregman's prediction can be adopted. Okay. So, if the grain boundary is very specific and the density is less, you go for Maxwell-Garnett, but if you see that the large inclusions are there, and in this kind of situation you can go for Bregman's theory. Another situation in which Bregman theory looks more realistic will be for the mixtures with large difference in the permittivities of the constituents. Something like if you have metal dielectric mixture, okay, where percolation phenomena above a threshold of the metallic phase takes place. So, in those cases you should go for Bregman theory. Now, if you do not know what this particular phenomena is, this is basically a threshold that is the critical metal filling factor, above which there is a formation of kind of long connectivity between the metal grains, and the optical response of the mixture will change abruptly. So, there is, if you are going for a metal dielectric kind of mixture, there is a threshold beyond which you should not have metal fill fraction. Okay. So, the last kind of the third type of effective medium theory that we will discuss today is the Nicholson-Ross-Ware method. So, this is a homogenization method based on the inversion of Fresnel formula. Now, if you remember the Fresnel formula allows you to calculate the reflection and transmission coefficient for the interface of two different materials of permittivity, of different permittivity. Okay. So, in this case you are using the reverse of it. So, you are based on the inversion of Fresnel formula relative to the transmission and reflection coefficient through the slabs of homogeneous medium. Now, this technique was conceived to estimate the complex permittivity and permeability of unknown material from the measured transmission and reflection spectrum of finite thickness sample. So, to do reverse engineering to find out what kind of material could actually provide this kind of permittivity and permeability. So, it was originally proposed in the time domain for pulsed measurement systems, and then it was adapted for higher resolution systems like frequency domain systems. Okay. So, the transmission and reflection spectra can be taken from the measurements of experiments, or you can actually get them by doing simulations. So, in this case what happens, a slab of thickness d of unknown natural or artificial mixture, something like this, that can be modeled as a slab of homogeneous medium with effective relative permittivity epsilon effective and mu effective, that is the effective permeability. So, in this case you are measuring what is the reflectance, what is the transmittance, and then you try to find out what is the effective permittivity and permeability that gives that kind of a transmission and reflection coefficient. Okay. So, it is supposed that the thickness of the homogeneous slab is equal to d. So, what you do, the complex reflection and transmission coefficients So, note that in Fresnel theory we used to use small r and small t for coefficients. So, here in this particular book they have used capital R, capital T for the coefficients, but you can also change them to small t to follow the continuity. Okay. So, what they do here, you have small r and small t or capital R capital T here. Okay, I am just talking about the reflection transmission coefficient. Okay. So, it is depending on gamma as well as some n effective. Okay. So, what is this n effective? It is basically the effective refractive index of the slab. So, it comes from square root of mu effective and epsilon effective. Okay. And what is k? K is basically the wave number, that is omega by c, and the reflection coefficient capital gamma is basically across the first interface between the input medium and this semi infinite homogeneous slab that you have made. Okay. So, you can see the gamma is basically taking of this particular form. So, gamma is basically eta effective minus eta naught over eta effective plus eta naught in the case of normal incidence, and you can also find out what is eta effective. Okay. So, from that this is basically the impedance, and eta naught is the intrinsic impedance of the input output medium. So, if from that you can calculate what is eta effective. So, I think there is a typo here, this should be n effective not eta, and this is eta effective. Okay. So, eta effective is correlated to reflection and transmission coefficient using this formula. Okay. And you can also find out what is the quality Q. Okay. And this particular Q is given as e to the power minus I k n effective into d. So, Q is calculated at T over 1 minus R n eta effective minus eta naught over eta effective plus eta naught. So, these are some formulas that actually tell you how to obtain n effective. Okay. So, I will not go into the details of this formula. The whole idea is to tell you that it is also possible to find out the effective permittivity of a kind of system which has got metamaterial kind of design, that you have inclusions or you have particles which are in arranged in this kind of a format. Okay. So, with this you can obtain epsilon effective and mu effective. So, what are the observations in this case? The first thing is that the choice of sign for the effective impedance and the refractive index does not alter the values of the effective parameters which are obtained via this equation. Okay. And there is some intrinsic ambiguity in the definition of this n effective. Okay. Because it is coming from this multi-valued complex logarithm and the choice of your branch order m. Anyways, the problem may be solved in very thin slabs in which the effective wavelength is much larger than 2D. So, this kind of method has been extended to characterization of mixtures in the case of oblique plane wave incidence for the study of spatial dispersion effects in metamaterials, as I was mentioning. So, this kind of techniques can be used for studying the effect of oblique plane wave incidence for spatial distribution effects in metamaterials. So, with that we will stop here, and in the next lecture we will discuss single and double negative metamaterials design, and thank you. If you have got any queries, you can drop an email to my email address.